So we started this kind of MDP kind of discussion, aiming to do what? And anyone has any view on why we started doing this kind of MDP reinforcement learning? Because ultimately we are trying to understand how any model, any language model, a visual model, visual language model, or visual language action model can be fine-tuned. Okay, that is the reason. And later into the lecture last time, I think we got into some initial stages of that kind of discussion. So the MDP problem introduced several kind of terms and also introduced several probability distributions. So that's why I'm kind of reviewing it to make sure that we all understand what's happening. So the probabilistic model that governs reinforcement learning is this, the one that you see here with this kind of random variables. There is a state that it is obviously, in many instances, it's going to be initial kind of state will be given in our language model will be, let's say, the prompt. But nevertheless, the environment will, the moment you have an action, the environment will transition to an S prime, which is via a stochastic transition sort of probability, via a probability distribution, and give you a reward, which is also random in a sense that your reward is going to be defined from a triplet of S, A, and S prime meaning the next state. Okay, so we have, we give you, if you like, a small example here in the kind of a grid world to understand, the stochastic kind of policy, the stochasticity of the environment, where 80% of the time you go into the intended state and 10% of the time you go to unintended states, and started defining this kind of reward function, which was basically an expectation, right? This expectation, I think it's kind of interesting to spend some time on it because, there is some kind of confusion with respect to what it represents. These expectations are obviously easy to write, like you obviously have a return at a time t. This return at time t is the random variable, because every time you have a conditioning, the left side of the conditioning is a random variable, the right-hand side are given quantities. You are in state S, you just took action A, you are going to be receiving a reward. And that kind of reward obviously is going to be associated with either in a game, for example, where the intended kind of state, like chess, for example, that the intended state is always kind of reached, or in our case here where it's not, then you're defining these reward functions such as what is actually shown here. And our aim here is to maximize the average return, as we call it. And this return is a quantity which is also needs to be kind of qualified a little bit, because it was presented as any kind of an infinite kind of sum from a t all the way to infinity, because the interaction may last for a very long time. And it was discounted because we wanted a discount factor to sort of incentivize the agent to either look for short-term or long-term benefits or gains or rewards, if you like. Now, I want to clarify that this is this GT is at this specific point in time is going to be one and another random variable, okay? Because obviously the future is uncertain, right? And therefore you can model, if you like, the GT with one random variable. Let's say could be a Gaussian. The GT plus one will be a different random variable. That's kind of important to recognize, because it will be, at the end of the day, we have in front of us, if you like, a random process, right? And the random process, if the interaction starts with from t is equal to 0 to capital T, this random process involves capital T plus 1, let's say, random variables, okay? And that's kind of a key to understand what's really happening and understanding the value function that we are going to present later. And of course, we defined also the policy as and the probability distribution, and we recognize the fact that stochasticity in reinforcement learning, MDP, is coming from two perspectives. One is a transition model, and obviously the policy, which is stochastic. Okay, and this policy is going to be, I will call it, with us until the very end, because policy for us will end up being a language model. Okay. Any questions before I go into the value functions that you want to ask? Okay. All right. So this is what I was mentioning a little bit about the nature of this kind of GT as being, if you like, a random variable, and GT plus one another random variable, and so on. So basically, what this value is sort of capturing is an expectation of this kind of random process, given the fact that you have a state S, right? So you can effectively consider that to be a conditioning on, let's say, someone is giving you some. Before we used to do regression, if you remember, at the very beginning, and effectively you can treat this as a kind of a regression kind of model in a sense. In what sense? If GT is, let's say, a Gaussian with some mean and some kind of variance, and GT plus one is yet another Gaussian with a different mean and another kind of variance. And in the more complicated case, the two are a joint kind of Gaussian probability distribution with some kind of correlation and some kind of covariance kind of matrix. This kind of conditioning reminds you something, reminds you the conditional mean that we were looking at regression problem as being the regression function, if you remember, right? So this S takes the form of X, and the Y here is actually taking the form of this kind of a multivariate Gaussian, let's say, right? And so what you have here is some kind of expectation of Y given X, which is exactly what the regression solution was, if you remember, many months ago. And so the value can be interpreted is exactly that, right? So the value of being in this kind of state. So another way to graphically kind of say that is that, obviously you have from this kind of a state multiple returns until you terminate, let's say, in this capital T box. And evidently the value of this kind of state is captures the average of this kind of returns. And we kind of went ahead and we accepted although the derivation I told you is in my YouTube channel, I'm not sure if you watched it, the Bellman expectation equation that effectively defines a recursive way, right? Where defines it like a bootstrapping, as we called it, way, where the value of future states are affecting, right, the value of the current state. So you can sort of think about this as kind of a problem where you're in a room and you divide the room into lots of grids, and each cell and let's say for the task of actually exiting, if you like, the door, if you take let's say an action and then you transition to any state of maybe the intended, maybe the unintended, obviously you gain something out of that kind of action, and that something is converted, right, to you gain or you lost. You lost something. It doesn't really has to be a gain, especially if the next state moved you a little bit further away from your goal, right? So you can think about this kind of situations where the value is function is assigns a value for each of these cells in the room, and obviously the cells next to the door are obviously commanding a higher value than cells far away from the door. Okay. So I sort of provided here some problem of estimating the value of the value function. Obviously, it's a function because it's a function of the states. So if I have, let's say, 11 states over here, I had in this kind of a small grid world, I have, let's say, 11, a vector of 11 values that I have to define, right? So this was basically the estimation problem or the prediction problem. Okay, and I just gave you a problem which is just write an equation for the based on the Bellman expectation equation of the value of S33. Okay, and we went ahead and we wrote this kind of equation, and then I suggested that what if we write the equations of all the other states or other remaining, let's say, 10 states in this kind of problem, and we wrote them down, and then we kind of try to summarize all these kind of 11 equations with 11 unknowns with matrix form that you see over here. But unfortunately, this matrix form involves some form of inversion, and I told you that every time that you see some kind of solution with inversion, to not really follow that kind of solution, but to try to come up with just like what we did in the regression problem back then, try to come up with an iterative kind of algorithm. It was stochastic gradient descent back then, that is going to approximate the solution fairly accurately for a small learning rate. Okay, so this I will call it iteration. I'm not so sure if we went through, but I wanted to just go. We're saving this for the review through the website. Unfortunately, I need to go back into here. Okay. So I wanted to just go through a very, very simple kind of problem of applying, if you like, this iterative kind of way of estimating the value function, because after we introduce, let's say, another value function, which is the state action value function, then this second value function may also give us the solution to act optimally in an environment because it captures the values of actions as well. Okay, that's the reason why we're actually doing that. We're gradually going into algorithms that are actually going to help us to find the pi star, okay, the optimal policy in any environment. Okay, so over here we have a deterministic policy. This means that this policy chooses just one action, and this action always transitions me. Okay, this is the simplest possible problem you can think of. And you only have two states, S1 and S2, right? And you have a discount factor of 0.9. And evidently, because you have a deterministic kind of policy, as I told you, the policy, if it is deterministic, basically one of the values will be 1.0 and all the others will be 0. So no surprises here about the matrix P for representing here the transition matrix, right? And so what happens now in this kind of reward that we'd like to evaluate, the reward function, if you like, in this case is if you go from S1 to S2, and you get a reward 2, and then you go from S2 back to S1 after you take the action A, the only action you can have, with reward of 0. Okay, and your problem here is estimate the V of S1 and the V of S2, or the value function. And over here you can see the solution, right? In the case where we have the matrix kind of inversion, and as you can see, the linear system of equations with two unknowns is resulting into V1 of 10 and V2 of 9. Okay. Now, the question for you is, just to try to make it a little bit more interactive, does it really make sense, the V1 to be 10 and the V2 to be 9? Does it make any sense? Okay, so it does really make some sense, because if I am in S1, right, in this kind of state as S1, then I have the opportunity to get a reward too. Okay, because anything I do, I will transition to S2, and then I'll get the reward too. If I'm in S2, in order for me to get a reward, I have to transition first to S1. So, although being in doing this kind of transition twice, let's say, obviously it will have a smaller value than being in just S1 to begin with. And that is the reason why the value on average over this kind of expectation is going to be the one is actually shown here. But I promise to show also the sort of iterative way, which is based on entirely on a concept of contraction. And the concept of contraction is recognized to be present when we wrote down the Bellman equation. As it turns out, the Bellman operator is a contraction operator. And what contraction means is that at the end of the day, you are going, if you start from some kind of a random sort of x, and I give you a very trivial example here. I took an equation which is similar to the equation we have in the Bellman, but it's grossly oversimplified. Xk plus 1 is equal to c plus gamma xk. So that is the equation. And I'm asking you to determine the x as the iterations are progressing for a gamma which is less than 1 and greater than 0. Okay. So this one, obviously, if you do that, and there's this very tiny kind of Python code in this kind of node, then you will actually see that this x is rapidly approaching the value of 20. Okay, and and this is basically the behavior, if you like, of this kind of contraction. If you start from some kind of initial kind of value x, you will converge to some fixed point. Okay, and the same thing will actually happen with the Bellman equation. Okay, so this is the proof in a sense that it's a numerical kind of problem now. So we have some kind of a state value function, initial one of all zeros. As you can see here, my V0 is all zeros. And then I'm going ahead and applying the equation, the vector form of this equation. V1 is obviously the R, the reward function, plus gamma, which I was given, times the transition model times the V0, right? So this is the V0 is a vector, V1 will be a vector by definition. Because of the nature of the transition kind of model here, we didn't type the transition matrix over here because it's diagonal. So and therefore we determine that the V1 will be 2 and 0. Okay, we go to second iteration, third iteration, fourth iteration. As you can see, after many iterations, the V pi is effectively converging to very similar values to the sort of closed form solution with a matrix inversion. Okay, so this was basically the rationale of this sort of iterative policy evaluation, is to allow us to, with numerical stability, to evaluate an environment, right? That an environment which we know a lot. That's why we call it MDP. We know the transition model and we know the reward function. Okay, and so obviously, moving forward, we will not know this kind of stuff, so we will need to try to find ways to estimate them. Okay, all right. So if there are no questions, we can actually go now to the second kind of value function, which is the state action value function. Okay, and the state action value function basically says the following. If you are in state S and you commit to make action A, so therefore there's an additional conditioning kind of term, then you are going to end up with a number, right, on average, right, that it is an expectation from S forward until your sort of interaction kind of terminates across many trajectories, if you like, infinite number of trajectories, in fact, that is actually going to be the Q, the number Q. Okay, so we will call this function Q function, and the previous function I'll be calling V function to separate them. So here, because we have the Q values for actions, I will actually claim that this Q function is very informative for me to, if I'm in this kind of state S, and I have some information about the Q values around me, to select the Q value, which is the largest one. Okay, and so this kind of a greedy behavior is definitely of interest in our path to actually provide a solution to finding the pi star. So we have called this we call this optimality. There were a couple of Bellman equations I didn't write that actually are becoming nonlinear, right? They have this maximization kind of term in there, but in terms of the rest of the componentry there, they are kind of similar, but because of this maximum terms over there, they are becoming from linear, nonlinear equations. And therefore, we have to now, there's no closed form expression, now we have to apply iterative methods to solve them. And policy iteration is a famous approach where we have sort of adopted here to demonstrate that there is light at the end of a tunnel, and there is a way to calculate the pi star for and the v star or the q star depending on the algorithm. Okay, so I went ahead and actually suggested to you to read this kind of recycling robot. And in the video, I'm actually going through that. And I hope you did it, because this gives you an idea of all these maximum terms over there. And then therefore the recycling robot had two states, 2 actions on one state, 3 actions on the other state. And therefore we were able to write the V star expressions out of these Bellman optimality equations. And I was asking you to write down the V star from the low state and the V star from the high state, because the states are low and high, as it has to do with the battery state of that kind of robot. Okay. So I hope you did that. This is a part of your website, so you can actually able to write down this kind of expressions, because someone may ask you to write down some expressions in English. Okay. Of course, you will need to understand all that in order for us to get into reinforcement learning, where we start to remove all these kind of assumptions of knowing everything. Okay, so this diagram over here, I have it also on the site and also on the video. It describes, if you like, this kind of policy iteration and this kind of contraction that happens, where you start with some kind of initial kind of policy and some initial kind of value, as we had it earlier, and then you evaluate the policy. You hit this line over here, then you evaluate, then for that policy, you act greedily, and you are going to converge into some form of a policy. If you not converge, you're going to define a policy out of that greedy sort of a behavior. Then for that new policy, you will again evaluate it, and again, and so on and so on, and at least you are going to very soon to converge. And I think in the video, I also have some kind of grid world over there example where I'm going through this kind of policy iteration. I'm also discussing another one, value iteration as well. But for now, let's focus on policy iteration for the interest of time. And if you understand that, you have an understanding of the MDP and how to solve it. And in terms of pi star and v star, that is, and get to define your optimal policy. So I hope you reviewed all that and you are in some kind of a good shape with respect to these equations of policy iteration and how they behave. And then we kind of transition to reinforcement learning. And in reinforcement learning, we said, okay, we do not know the P, the transition model. We do not know the reward model. The only thing we can do in Monte Carlo kind of methods is to, we cannot do bootstrapping. We cannot really do bootstrapping because we cannot reach states that can obviously be reached from, or even know that there are some states S primes that we have not seen. Over here, we are kind of myopic. We only thing we can do is see the state we're in right now and take an action, and then transition to another state as prime, and then take another action, transition to another state as double prime, and so on. So we are effectively, as compared to the previous kind of MDP kind of solutions where we are doing breadth first type of free expansion, over here we do it depth first expansion because we can't really expand in terms of breadth. So we are forming trajectories the orange trajectory and the magenta trajectory and so on. And out of this kind of trajectories, we have to start storing all the data that the experience that we had in this kind of environment. We store everything. And then we go and start counting how many times I have visited the state and what I have seen after visiting that kind of state from the actual behavior, right? So the actual data that I have stored, okay? And this is basically the equation of over here that allows me to get the actual returns until I terminate it for each of the kind of trajectories that this state is part of. So, and then obviously at the end of many episodes, I have now an estimate of the number of times that I've gone to that kind of state and the number of returns I've seen from that state until I terminate. And therefore, I'm defining now an approximation to the value of being in that kind of state as obviously the sample mean of the returns I've seen from that state. And then I basically made remember that I've seen this kind of sample mean as a kind of an estimate that I need to recursively kind of update, incrementally update, I should say, not recursively, incrementally update when we're discussing Kalman filters. And at that time, I was presenting in one video the localization, the drone localization kind of problem, and I was telling you that starting from some first principles of the maximum likelihood of a Gaussian random variable, then the best estimate for that is the sample mean and of the mean of the Gaussian random variable is a sample mean, and so I wrote down an expression back then that allows us to estimate the new mean, the new sample mean from the old sample mean plus gain. I call it at that time gain factor, though it isn't, which was stood for 1 over k in this case, times the difference between the xk minus xk is the new information, the new sample that is actually coming in, minus the previous sample mean estimate. So here, for every new sample that comes in, I'm updating the sample mean. Okay, so for every time I'm visiting this kind of state, I'm updating the sample mean of the returns from that kind of state. That is a connection between this and this over here. Okay. The two. So I have a sample mean estimate. I'm now updating kind of incrementally, and therefore I wrote down this V pi of S as an update equation, okay, where alpha over here is 1 over ns, the number of times that I visited this as described in the mu equation over there. And the new information is the sample return that I got from that kind of state onwards. Okay, and obviously this is the incremental, this is the old sample mean, and this will give me the new sample mean. Okay, that's basically it. This equation with this kind of difference is kind of an important equation because we will see it now in front of us on the second major method that it is called a temporal difference kind of method. And this Monte Carlo method, it will define for us a method, a reinforcement learning method called a reinforcement kind of algorithm that will actually give us the ability to change the parameters of parameterized now policy in the case we have an LLM and be able to sort of optimize that kind of LLM by changing its parameters a bit later in this kind of discussion. So before we go there and see how the Monte Carlo method is actually used in this kind of reinforced kind of algorithm, the second kind of method that we have looked at is this temporal difference method that tries to sort of attack a little bit the pain points about Monte Carlo. And one of the major kind of pain points of this kind of Monte Carlo kind of method is that I have to terminate first before I'm able to know anything. Okay, I cannot really learn my sample return before I terminate. And for that kind of reason, while I'm actually acting in this kind of environment, I'm going from one state to another, I'm getting a lot of samples, but these samples have typically large variance in terms of rewards. And they have, but because they have, if you like, I'm aggregating quite a lot of samples, I have smaller kind of bias. Okay. So I'm trying to attack the variance thing, because the variance seems to be the reward variance seems to be a very key component of efficient training, and if not efficient, at least training that can converge to something. Reinforcement learning training kind of algorithms are also not very, I will call it, stable. So we're trying to attack all variance kind of factors for them. And the temporal kind of difference method that we introduce over here, that is basically what proximal policy optimization is doing, is based on the previous equation, the Monte Carlo kind of equation, but instead of the sample return, we don't wait. Instead of the sample return, GT, what we do is we are updating with what we call a TD target, replacing the sample return with the one-step unrolling rollout kind of sort of reward plus an estimate of the value after that kind of a single step. So we basically learn as we go. We update the value of a state from any information that the immediate states can actually provide to us. So we're trying to combine the kind of the bootstrapping kind of method. So here we are not really making any strong assumptions about knowing the reward functions and knowing, if you like, the transition model and so on. So from whatever state we ended up and whatever value that state had up to this moment in time, we take it, discount it, sum it up with this reward that we have, and this TD target is going to then replace GT, and the remaining equation is identical with what we have in Monte Carlo method. Okay, so we have, in fact, the ability to, and I gave some kind of example of that, the ability to do what is called the TD of 0, where lambda is equal to 0, and lambda now is a new variable that allows us to somehow weigh all this kind of potential returns that we're actually going to get if we do not update immediately, but we wait multiple steps until we update the form, if you like, the TD target. So we may allow, if you like, just like what the equation is actually doing over here, n steps to elapse before I do the update of the TD target and estimate, if you like, some kind of return from that. So the TD target now is the return after n steps. I know the return because I'm waiting and I'm aggregating all this kind of data, which is takes a form now of rewards, actual rewards, and then at some point I update the value of that kind of state using exactly the same equation. Okay, and this lambda is, if you like, a scalar kind of quantity that allows me to weigh in this kind of way that's actually shown in the diagram, this kind of individual returns. So I may weigh the first return, a little bit stronger than the other returns that are coming in towards the nth kind of step as I progress towards the nth kind of step. And in the limit, if n is becoming capital T, then I'm back to Monte Carlo. And if n is 1, then I'm going back, which means lambda is equal to 0. I didn't write the lambda expression over there. Then I'm actually back to TD of 0. Okay, so this allows me to move in between TD of 0 and Monte Carlo. So the whole game here is how we are attacking the variance. So as it turns out, the TD algorithms, because they are doing they're using a smaller number of samples to estimate and update the value function. They have smaller variance, but they do have a larger bias because of the number of samples. They are much more limited compared to the much larger number of samples in the Monte Carlo methods. Okay, so but nevertheless, they tend to behave better. Okay, and then we kind of went into, okay, so we have now some estimate of the value functions, and either V or Q. The Q is sort of goes identically to what I described kind of for the V. And then now we can actually see whether or not we have the ability in reinforcement learning to do control. And control is choose a policy. I'm giving you the V, what kind of control? Before, the control MDP was greedy. And here the control is still going to be sort of based on this kind of algorithm that is going to allow us to act a little bit differently than just pure greedy. Okay, so we'll describe that when it comes to understanding the PPO and the associated kind of usage of PPO in LLMs. And LLMs in our discussion here will be VLAs. So before I go to this, I went to this kind of control, and we kind of looked at two major categories of reinforcement kind of learning problems. One is this on policy kind of algorithm, which basically means that the same policy is used for acting and for learning, sort of how to do the control. So the same policy is used for generating, if you like, the training data and finding the kind of optimal kind of policy after that. And the off policy, where a different policy is used to learn the training data, and a different policy finally is being produced as a control policy. Okay, so this pi is going to be with us for the on policy, but when we talk about off policy, you will see letters like mu, nothing to do with the sample mean, but it's just a common letter to describe the sort of the actor kind of policy, and the pi, which is the previous kind of letter we had for the policy. Okay. Any questions up to this point before we kind of progress a little bit? Okay.
No questions.
Yes. Oh, no questions. Okay. All right. Okay. I have. So that you should recognize now that we went into this kind of fine-tuning of LLMs, VLMs, and VLA. Now, fine-tuning with reinforcement learning is becoming a major kind of capability set that engineers should have, computer science should have. So I think you should get something out of this course in general, especially if you're looking to go into robotics with Levin's kind of policy or pi zero and stuff like that. We don't have all the time. In fact, we have no time to go through all these kind of details. But I hope in this course you got some kind of foundations out of it. So in general in AI, there are two trends that I want to mention. One is that the computer, if you like, the architecture is kind of not necessarily being the best usage of time or research time these days. Despite the fact that plethora of architectures and trials and things like that, the transformer kind of architectures are sort of a pretty sort of prominent there, and we do not see a lot of variability from, let's say, decoder-based architectures. The loss functions are becoming a major kind of factor for performance improvement. So what loss are you going to be using to even do pre-training? Obviously in computer vision and therefore also in robotics, you have significant advances with this, in terms of self-supervised learning. And then, of course, when it comes to fine-tuning, as it turns out recently, I think to some degree, the recent model from DeepSeek kind of went into that kind of direction and provided some kind of manifestation of what I'm going to say here. But reinforcement learning becomes probably one of the main avenues of companies have that cannot really have the resources to compete with or to build their own kind of models to tune these kind of models to their kind of business and organizations. So in reinforcement learning and fine-tuning reinforcement learning, there are two stages that are typically done. The one is called preference fine-tuning, and there we have the ability to instruct the model to be to produce trajectories which are better, more preferred from humans and the users of the system. And the other is the reasoning, where effectively we are able to let the model allows the models to actually reason, let's say solve mathematical problems, for example, and other kind of reasoning, take other kind of reasoning steps. And of course, we have a lot of algorithms behind this kind of last two boxes, okay, which obviously we don't have time to go through all of them, but I'm just going to convey foundations of PPO here. So we have the, if you like, the tree again that we saw first in MTP kind of problems. And I was telling you that we, in this kind of space, in this kind of domain, we start from the initial kind of state as zero, which is basically our prompt. And we have a policy that is now parameterized by theta. And this policy theta is now going to be our LLM. Okay, and in the simplest kind of possible case, we only have, let's say, tokens. But in the case of VLA models, we have, tokens that are coming from not only what the sensing kind of architecture of a robot is actually giving us, let's say cameras and things like that, lidars and stuff like that, but also we have language instruction, and that is coming at the input. And of course, this means that the instruction is happening for producing at the output actual actions. Let's say, obviously, actions are going to be, could potentially be discrete, but in general, they are continuous actions, continuous random variables here. But nevertheless, over here, we see some kind of a first instance of a P model, which is kind of discrete, and it produces some kind of posterior probability distribution, just like what we have met earlier at the output of y given x comma theta, and this is going to be just the vocabulary size, let's say, okay, the size of this posterior probability. So it's pretty substantial probability distribution, and the action that is coming, that is we saw earlier, being the agent being taking an action, is in the case of a non-robot kind of agents, is going to be just pure LLM or even VLM is going to be the next token, the token that it is going to be the produced at the output of your screen, which of course is going to then to be appended with a prompt and then form a state S1. At that time, you may get a reward or you may not. In many instances, you don't get a reward because no one is going to give you rewards or other than zero with the first token. Obviously, you may have a model that either generates some kind of thoughts in this kind of reasoning kind of process, or you need to wait until the model is giving you an output, a numerical, let's say, output, if you're solving some kind of a reasoning kind of problem, and then you can give it a reward of, let's say, one I wrote over here at the end. This basically when the interaction kind of terminates, and you have not only the output of the original kind of prompt, but also you have the complete completion of what is being generated. Okay, now out of this kind of reward that I'm actually going to be getting, I need to find a way now to update my parameters of the pi theta. Okay, so do we understand a little bit the problem setting here on this? Hopefully everything is kind of understood. So with that kind of said, I wanted to now present the sort of an algorithm which is called reinforce, right? And if you go to the website, I kind of typed okay, what is the Okay, here we are. We are in reinforcement kind of learning. So it is basically the foundation for all algorithms that we are dealing with, and that's called policy gradient algorithms. And if we understand this reinforced, we're able to understand the PPO, okay, the proximal policy optimization. So we have to start from this kind of algorithm, and we are going to understand how we will update the pi theta, okay? And obviously we need a loss function for updating that. And we are going to just look at this loss function, how it is formed step by step, and then we will look at the training of this kind of reinforcement algorithm and apply it. We're not going to talk today about the application. The application here is kind of a toy kind of example, but the application obviously is going to be done for us in a far more elaborate Python code that it is associated with fine-tuning a language model. Okay. All right, so let's start from this kind of policy gradient. Okay, so we are effectively trying to do the following. Okay, in all algorithms that we're going to be dealing with. So let me just write it over here.